From the Canterbury University, UK. I think his topic is focusing on the how to design multi-component catalyst and integrated reactor system. I think it will be very interesting. So please, Professor Osman, let's welcome Professor Osman.
Good morning, everyone. Thank you, Professor Tian, for inviting me to speak in such a great event and in such a great city as well. So I came from Canterbury. This is in Kent. This is known as the Garden of the UK. But when I came here, I found Shindao is such a magnificent city as well. So my name is Ahmed Osman, Senior Lecturer in Energy Engineering in Canterbury University. I'm also a distinguished editor in environmental chemistry editor. And the good news is the new impact factor of that journal was released last month and it is 20.4. So if anyone working in environmental chemistry, you are so much welcome to submit your paper there. My talk today is about designing multi-component catalyst and integrated reactor system for ultra-low temperature methane combustion and PME production. From mechanistic insights to holistic LCA and economic evaluation. So we all know about the climate emergency. So since we disturbed the climate, the CO2 cycle, the carbon cycle, the carbon dioxide concentration in the atmosphere have dramatically increased from around 280 parts per million in the atmosphere to now more than 400. And we can see the consequences in the fire, drought, and economic loss as well. So I'll talk very briefly about the strategies to mitigate climate change. One of those strategies is called conventional mitigation technology. So conventional mitigation technology, such as using nuclear power, renewables, carbon capture and storage, and also fuel switch. Fuel switch when we switch our fuel from burning like coal to a cleaner combustion fuel like natural gas and biofuel. So my first part of the talk today is about syngas production, so which is the catalytic partial distillation of methane. And in this case, we take the methane and we produce syngas, which is carbon monoxide and hydrogen. So the first part of our work here, we've done some literature review, like Martino, Zhu, Shah et al., and to see what is the temperature in the literature our colleague working on, and you can see the temperature is around 600 degrees. So our aim is to go for 390, so 200 degrees below that working condition in the literature. And also the space velocity, so it was around from 4,000 to 60,000. So our aim is to go to 63,000 space velocity. And when we consider the catalyst component here, so you can see that we decided to go for nickel. Nickel is the most active metal in this reaction, but nickel has a problem, the tendency to form coke and deactivate after a while. So, and then we use series of conjugate. We want to have an auto-clean catalyst. That catalyst can clean itself if it forms any coke by using the serial side in this catalyst component. But the problem with serial side, it has no surface area. So that's why we use the third component here, which is the acidic type catalyst, which is alumina. In this case, we found that eta alumina, this is one phase of alumina like gamma, eta, alpha alumina, and eta alumina we found it very effective in this case, in terms of acidity and surface area. And also we use zeolite. That is some 580, and support to improve the dispersion and acidity of this catalyst. In this catalyst preparation, we use co-precipitation and sonication. So co-precipitation to allow small particle size and strong interaction between the naked and the synchron. And also we use the sonication. We found that sonication is really helpful in methane total combustion. So we want to try the sonication here after doing elimination. And this is our prepared catalyst in this case. We prepared two-component catalysts like nickel or aluminum or nickel with zeolite or nickel or series equipment and an oxygen storage capacity. And the three components together with either co-precipitation or doing elimination. And what we found here also when we've done the surface area, we tested the surface areas and porosity of the produced catalyst. We found that, of course, the alumina has a large surface area, and the light has 425 meters squared per gram. And when we done the combination of the three components together, this is the surface area and porosity. For this is an STL image of the produced catalyst, and you can see here in the eta alumina based catalyst, it form larger, smoother particles, and in the light it starts to form small particles as more bubbled particle of larger surface area. And when we use just series zirconia here, you can see it form a larger bulk particles with low surface area. And this is expected, of course, because series zirconia has low surface area. And we've done also some characterization like XRT to understand the morphology of surface and bulk of the produced catalyst. And of course, TPR, temperature control reduction, to understand the reducibility of the catalyst. And you can see the three component catalyst here, naked series zirconia alumina, with oversaturation, has a strong interaction between series zirconia and alumina. And of course, we've done some surface chemistry here, like XPS, to understand the oxide phase on the surface. And both naked and series show a number of oxidation states, showing a facile reduced behavior of this catalyst. When we done the catalytic activity at 390 degrees, from 350 up to 700 degrees, you can see now we reached the equilibrium line with the three component catalyst. If you see here, naked on alumina, the two component catalyst show the lowest activity. succeed? You know, when you cook a food in the stove, what you're doing is you're doing dehydration reaction. Okay, you cook the food, they combine together, and you lose water. This is the same here in DME. But in DME, you cook methanol. You take methanol and you cook them, and they join together to form the dioxide DME. Okay, and you lose water, of course, from this reaction. So we've done some reaction for the production of DME from methanol. And as I said, methanol could be used in transportation. And China is the first producer of that fuel, which is a very combust. It's a blue type fuel, and very clean when it combusts. We've done some reaction there to understand the mechanistic of producing DME. Like here, as I said, this is a cooking type reaction, dehydration reaction. It means if I make my catalyst hydrophobic, like a water-hating catalyst, it can repel the water, so it can resist the deactivation during this type of reaction. And this is the water catalyst. You can see this is hydrophilic. Hydrophilic means loving water, and this is hydrophobic. So the type of catalyst that reject water or hate water. And we found out that when you prepare alumina as a hydrophobic alumina, it works very well in this type of reaction. And to understand the mechanism, we use in situ drift reaction here to at a different temperature from 50, 100, 150 up to 250 to understand the surface chemistry with the intermediate forming at that type of reaction. And of course, we use in situ drift here to understand acidity in terms of Lewis and different types of acidity and TEM. Here, as you can see, we use silver on alumina. You can see the silver atom sitting on the dispersing on the support of alumina. Okay, this is my last part of the talk, which I will talk about how to design a holistic decarbonization system. Everyone is talking now about climate change, decarbonization, net zero. So how to design a holistic decarbonization system based on something like negative carbon technology like biochar. Okay? So you can apply this approach in any type of action, in energy or any type of thing. It doesn't apply only to biochar. It could be used for any type of reaction, energy or climate change. So first of all, we have product optimization. So what is the optimum condition to produce biochar here? What is the best condition to have high surface biochar porosity and carbon stability? And if we take it in an energy type talk, what is the best parameters and operating parameters in such a reaction to produce a biofuel? So once you do that product optimization, you can go to the characterization now. You characterize the catalyst for your product. Once you are happy with this, you can do process modeling. This is an aspirin modeling that we've done for the biochar to answer a very simple question. If we produce biochar from agro waste, is this process self-sustained in terms of energy, or it needs energy from the outside? So we've done the process modeling, and we found that we have an extra energy produced in such process. Once you do this process modeling, you can go to the LCA, Life Cycle Assessment. This is to test the environmental impact. So everyone is talking about sustainability, but no one is measuring it. Like if I'm saying that my process is sustainable or green, how much green? How many tons of CO2 you remove from the atmosphere? What is the impact, real impact, environmental impact of your process to the environment? So this is a life cycle assessment. Once you do the life cycle assessment, now you can go to the economic modeling. I came from a chemistry background, but through that journey, I've learned a lot about the economic modeling. Like, because when you have a technology, you come with a very simple question. Is your process feasible or not? If it has been commercial, it's going to make money or not? So I have no answer at the moment. So that's why we decided to include one member of my team to focus on the economic modeling. Economic modeling like NPV here, NPV, net present value. Net present value, this is a point in your company that it's going to make money. If you go more, it's going to make money. If you go less, you're going to lose money. This is the point where you can say that your process is feasible or not. And I've learned a lot during this journey, like MPV, IRR, simulation, Monte Carlo, tornado diagram. Like this is a very, very nice branch where it's integrated with the chemistry here. So in this case, we've taken the olive tree pruning to produce a biochar, but we've designed a holistic decarbonization process. We call it techno-environmental economic process. Like this is a technical, environmental, and economic. Techno-environmental economic process. And when you have such a holistic, multidisciplinary team, it's very easy to publish the work. Like we have this work, producing biochar on a large scale. We took Spain as a case study, and in this case, we've designed a large-scale biochar plant that it can process biomass with a capacity of 6.5 tons per hour. And the LCA here showed that we can remove with this factory 24,000 tons of CO2 equivalent annually per year. And the profitability achieved at a price of 110 euro per ton of CO2 and 350 tons per biochar when you sell the physical biochar. And this work has been published in the Journal of Fuel Production. As I said, like, if you take this idea, taking olive tree pruning, producing biochar, the idea is not novel. But when you integrate such techno-environmental economic process, this simple idea becomes novel now, and you can publish it very easily in high impact factor journal. In such a case also, if you look at the e-fuel, like e-methanol, I've read in January this year that there is a factory that has been shut down in Europe of producing e-methanol. Why? Because the economic doesn't work. It's not feasible. But when you look at the production of methanol and you integrate different types of process, it can work. You can increase the energy efficiency of the overall process. Like for instance, I can use a biogenic source like agro waste, anaerobic digestion to produce the CO2. Okay? I can use wind, solar, and water electrolysis to produce hydrogen. When you combine CO2 and hydrogen, now you can produce the e-methanol as e-fuel. What we've added here to this fuel supply chain that we can also use oxygen. When you water electrolysis, when you do water electrolysis, you not only produce hydrogen, you produce you produce oxygen as well. So that oxygen is waste. We call it waste oxygen. So what if we use that oxygen waste in wastewater treatment plant? Now we have a use for one of the waste. Again, when you combine CO2 and hydrogen to produce e-methanol, you are producing heat. What if we use that heat in heating molasses tank, for instance? Reaction. But methanol have a low calorific value. Yes? So we have to combine it, we have to blend it with diesel. Okay? So this is the second part, the work in engine work. We use machine learning here to optimize that mix. Because when you have different types of mix, I have methanol, like here. I have methanol, I have diesel, and I have surfactant, because methanol and diesel, they don't mix. So we have to add surfactant here. But we have different ratio here. What is the perfect mixing ratio between methanol, diesel, and surfactant? So we use here machine learning to optimize that ratio, and we've done some testing in that dual fuel methanol diesel blend. And we found that we have 12 novel methanol diesel blend achieving up to 90% increase in the PB and so on. So, and our machine learning have a prediction accuracy of 93% of that type of methanol diesel dual fuel blend. You can see also, we try to do research with an impact. Like the research that it doesn't have, like as Professor Tian said, golden paper, like to have them in the real application. And this is a big project that we participated last year called Green Shipping Corridor. This is the project where they want to have all the ships between Belfast in Northern Ireland and Liverpool to run on a ship of clean fuel. So we introduced that blended diesel, miscible diesel blend, and we are trying now to test it on a commercial scale. And hopefully by the next year or this year, we're going to have a very encouraging result of the real application of this miscible diesel fuel blend in a real ship between Belfast and Liverpool. And that photo was taken last year in the closing event with the UK Maritime Minister, where he supporting that type of work and want to have it in a real ship very soon. So in conclusion, so we can say low temperature methane activation was successfully achieved through strategic multi-component catalyst design, where preparation methods like co-precipitation versus wet impregnation and the component synergy were critical to perform synergistic interaction between naked series zirconia, zeolite, and alumina. In total methane combustion, we use a 4-component catalyst, where palladium here was the active component, platinum to stabilize palladium, and titanium was used for oxygen storage to enable that cycle of palladium oxide to vanadium, and acidic support alumina or zeolite to facilitate the CH bond dissociation. This system was further integrated into a photocatalytic platform, enabling potential deployment in real truck after treatment unit for ultra-low emission zone. So we can say here that pollution becomes potential when science meets purpose. A novel reactor in reactor design, the reactor design was introduced, where exothermic methane combustion drives the endothermic steam reforming, improving thermal integration and hydrogen-rich production. The platform was extended to DME synthesis and the biofuel from agriculture based using acid-type catalysts like eta alumina. And we studied the mechanism here using in situ drift reaction and other spectroscopic studies. To ensure practical scalability, a holistic decarbonization framework was applied using techno-environmental economic modeling, integrating reactor design, LCA, and profitability threshold. And finally, in dual fuel innovation, machine learning was employed to optimize, now being trialed in real marine vessels between Belfast and Liverpool. So, yeah, and last word here I would like to conclude with, when combustion is reimagined, it fuels not just engine, but solution for the future, and the world needs more of this reimagination. Thank you.
Okay, thanks, Professor Osman. I think we are just out of time, so for the questions we can have at the coffee break. Okay. Certificate.
背景你去掉。
是我中间来的。OK。
I think now we have corporate